Acid-base. In this lecture, we're going to talk about acid-base titration. Now, what is titration used for? It's used for to find a concentration of an acid or base from a known concentration of an acid or base. And we do this by basically not diluting, but neutralizing the acid or the base. Okay, we're going to find a point where we find something called the equivalence point. The equivalence point is where the amount of acid equals the amount of base, so they can basically neutralize each other. So there are three types of acid-base titration. There's a strong acid, strong base, which is the easiest one. Okay. There's a titration of weak acid and a strong base, and a titration of weak base by a strong acid. Okay. So either of those, they will work. It's fun. It's really good. So a strong acid-base titration. So if you look at this, it says that 3.0 times 10 milliliters of 0.5 molar HCl is titrated with 0.5 molar NaOH. Notice that we know how much HCl we have, and we know the molarity of that HCl. We know the molarity of the NaOH, but we don't know how much of the NaOH we have. So by doing this, we can know how much. So for example, the net ion equation is, of course, at the bottom, H plus OH minus makes H2O. So that's the equation. So we have to find the initial pH of the 0.5 molar HCl, the pH after 10 milliliters of NaOH added. Okay, remember, every time you add NaOH, we're adding OH, we're neutralizing the H+, and then of course 30 milliliters and 50 milliliters. All right, so we're going to go through that. So first, we're going to find the initial concentration of H+ to find the pH. Now remember, strong acid dissociate completely, so the HCl will become H+. So whatever amount we have as HCl, we have the amount of H+. So the amount of HCl we have is 0.5 molar, so that means we have a 0.5 molar concentration of H+ also. So to find the pH, we find the negative log of the 0.5, which is the pH of 0.3. So now what we're going to do is we're going to find how much, what is the pH after 15 milliliters of titrant are added. Titrant is basically the base in this case, right? So first, what we're going to do is we're going to find out how many moles is 15 milliliters of the OH. Okay, so here we go. So we have 0.03 liter solution, 0.5 liter solution over 1 liter. This is molarity, right? That means we have 0.015 molar of HCl. So if we place that into 15 milliliters of the titrant at 0.5 molar solution HCl, we're going to produce 0.0075 molar of NaOH. So this amount of NaOH is going to cancel a certain amount of the HCl, neutralizing the H+ that is released when the HCl breaks up. So here's the ice chart that shows that. So at the beginning, we have 0.015 molars of H+ from the HCl, and we have 0.0075 molar of OH from the NaCl. So we have no liquid created. So now, of course, the change is we're going to use up all the OH, right? So this H+ is going to be subtracting the concentration of the OH because it has been connected, it's been basically bonded to create the water molecule. Okay, so we have some of this left, but we have none of this left. So at equivalence points, we should be 0.015 subtract this, it's equal to this, right? So notice that this is half of that, so basically we have half of it. So now if we have the H+ concentration, we can actually now plug it into the negative log concentration and find that, right? Now, because we added some more solution, milliliter solution in NaOH, we have to add that to our solution. So the volume is now changed. So now, because we have a new mole, we have a different volume, we're going to have a different molarity. So once we have the molarity, that's the concentration H+, we can plug it into the negative log and we change. Notice that the pH has actually gone up because we neutralized some of those free hydrogen ions that's been floating around. So find the pH after 30 milliliters of NaOH were added. So we're going to do the same thing again, okay, just like before, and then we 30 milliliter of NaOH, okay, was added to the 30 milliliter of HCl. So we're going to find out what's the molarity of the NaOH, and then we're going to basically subtract that from that. So in this case, because we have the same, notice that when you do this, the molarity of NaOH will equal the molarity of the OH, okay, I'm sorry, of this hydrochloric acid. So all the H+ in the HCl will be used up, and this is what we call the equivalence point. The amount of hydrogen ion is equal to the amount of hydroxide ion. So now they're neutral. So because there's no longer hydroxide ion or hydrogen ion in the solution, the pH is now only 7. Okay, because why? Because remember, they're all neutralized. They're water now. All right? So what happened? We put in a pH. What is the pH after 45 milliliter? Now notice that 15 we basically neutralize half. At 30 we neutralize all of it, and now at 15 we should expect to have a lot more OH left over. Okay. So again, we do the same process as we do number 1. We find the moles of HCl created. Then we find the moles of NaOH or the OH created. Then of course we use the ice chart to reduce those amount. And because now the H plus is going to be the limiting, we have no more H plus, but notice now we have OH minus. And because we have OH minus, we now have POH. Now don't forget that we have to add up the volume and divide and take that volume, and we take the moles divided by that volume to find the concentration. So the new volume is now 0.3. That was originally from the H plus, and the 0.45 liters, 0.045 liters, that's from the NaOH. Okay, so now the new liters is 0.075. So we take the 0.008 here when divided by 0.075 liters to find basically it's 0.1 molar. So that's 1.1 molar of the OH. So of course we can find the pH or the POH of that, which is 1, and of course the pH of that would then be 13. Now if you look at the graph here, you see a strong acid, strong base characteristic. Okay, so notice the change in pH does not change a lot until you get so close to that equivalence point, and boom, it changed really fast. So when you graph this is what you're going to see. So for every single drop of NaOH put in, it's going to change drastically. But once the change is over, okay, notice that the pH balance out. So in the middle of this graph, the middle of the height of this increase is what we call the equivalence point. The point at which pH is equal to 7, and that concentration of the NaOH is now equal to the concentration of the H plus. So let's take a look at the weak acid and a strong base. Now remember, a weak acid is not going to dissociate all of its H's. All right. So here we have 3 times 10 molar milliliters of 0.5 molar acetic acid is titrated with 0.5 molar NaOH. The K for the acetic acid is 1.8 times 10 to the 5th. So we're going to find the initial pH of the acetic acid. We're going to find the pH after 15 were added, the pH at equivalence point, and the pH when it was 4 times 10, which is basically 40 milliliters of NaOH were added. So if we look at the titration reaction, we have acetic acid add the OH. Notice acetic acid doesn't break apart, so we keep them together to make acetate plus water. Now, equilibrium between weak acid is conjugate base. Okay, so again, this is the second part to it, right? So this is the acid part that actually breaks apart. So to find the initial pH following the simple method, we use this. Now remember, because we're using a weak acid, we have to use the ice chart to see how much actually comes out. So we know at the beginning there are 0.5 molar of the acetic acid. There's no H plus and no acetate. Then of course we subtract the amount of acetic acid that will break down to H plus and acetate. Then we combine them together in equilibrium. And then of course we plug it into the equilibrium constant Ka. Then we plug those functions in. Okay, now again, we have this quadratic, and because the Ka is very small, we can actually reduce that, right? So we don't need that anymore. So then we solve for that, and so we know that X is 0.003 molar. And because X is 0.003 molar, that's how much the H plus concentration will be. So the H plus concentration, we basically use that to put in the negative log, and we find the pH of acetic acid will be 2.52. Now, let's titrate this with 15 milliliters of NaOH. So now we know how much, we need to know how much moles of acetic acid is in that initial concentration of acetic acid. So we know we have 30.3 milliliters of loose solution. We know that it is 0.5 molarity. So that means we have 0.015 moles of acetic acid. Now, the sodium hydroxide, we know it's basically dissociate completely, so 0.105. Half a mole is 0.0075 moles of NaOH. So now all we have to do is place it into equation. Now remember the acetic acid, that's how much OH we have. Acetate we should have 0, okay, because it's going to be, there's no acetate coming out of here, and water we don't know, or we don't care. Okay, so here we're going to subtract this because the OH is going to be limiting. We're going to add the acetate here. So now that's how much we have left, because this is half of that. We have no more OH, and now we have basically 0.0075 of the acetate that is created. Because remember, this H goes there, right? So now, the new volume, we have to add them up. and we have the molarity here. So from the molarity and the new volume, we should have concentration. Okay, so the acetate or acetic acid concentration is 0.17 molar of acetic acid, which means the acetate concentration is also the same because it's a 1-to-1 ratio. Now, we're going to put it into the Henderson-Hasselbalch equation, right? Because we have the acetate concentration and the acetic acid concentration, and we know the pKa also. So by placing this in, we should be able to find the pH of this solution, which is 4.74. Okay, so now we find the pH. Once we find the pH of this, okay, the equivalence point is reached when equal numbers of moles of the sodium hydroxide and the acetate have been reached. Okay, the acetic acid have been reached. Now, this occurs when 30 milliliters of 0.5 molar NaOH is added to 30 milliliters of 0.5 molar of the acetic acid. Notice if you do this, the moles comes out to equal. And once it equals, that means you are at equilibrance point. Okay, that means all the OH that's created from the NaOH will be connected to the H's that was created from acetic acid. Now, only sodium and acetate remain in solution. The other part is water. Okay, so water. So now the water, remember, the acetate, because it was a weak acid, like has acetic acid, becomes a very strong base. So a strong base, what it's going to do in the water is going to rip up the H from the base to create acetic acid and hydroxide again. Now that's the weak base part of it, the weak acid part of it. Right? So now I find the pH equivalence point. So now we need to find the Kb of that point. Okay, so we want to find the Kb. So we know that the Kw is equal to Ka is equal to Kb. So Kw is 1 times 10 negative 14. The Ka is 1.8 times 10 negative 5. That's given to you. So the Kb must be 5.6 times 10 negative 10. Okay, so now of course we can find the pH of that if we want to. Okay, but find the moles of acetate. So here we go. We found the moles of the acetate by finding the molarity of the acetate, and that's the many moles. So 0.015 moles of acetate in solution as all acetic acid is reacted. So here, no more acetic acid is left, only the acetate. So find the acetate concentration. So again, we have to find the new volume that is added. And from the new volume, we can divide it from the moles of the acetic acetate to find the concentration of the acetate. Then we put into the ice chart. So at the beginning, we have the acetate as 0.25. Remember, there's no acetic acid left. It's going to react with the water, but this is liquid, pure liquid, so we don't worry about it, to create acetic acid. So here, we're going to subtract x and we'll plus x. So, of course, 0.25 minus x. This is now x and x. So now remember, we're at base now. We're at Kb now. So we're going to place into the Kb reaction. All right, again, Kb is pretty small, so we can get rid of the x on the bottom, so we can do the work. So concentration of OH is 1.2 times 10 to the negative 5. So of course we're going to plug that in to find the POH, and once we find the POH, we can find the pH. So solution is basic at equivalence points. This is expected as there is a basic anion in solution. So notice that in a strong acid and strong base, the equivalence points will produce a neutral compound. Okay, but in a weak acid and a strong base, you're not going to have that. Because the base is stronger, you're going to produce a strong base, a basic solution basically, at equivalence point. We'll continue this in the next lecture.